Okay, we're going to go ahead and do a new test, still in the chi-squared family. It's just an extension to the chi-squared goodness of fit. And so we're going to start today with the chi-squared test for homogeneity. And next class, we're going to do the independence portion of this. So, the chi-squared, this, and by the way, is on page 10 in your chi-squared packet, your chapter 26 packet. So page 10. All right, the chi-squared test for homogeneity is one where we are testing to see if items happen at the same rate. Homogeneity, of course, meaning the same. So groups that are homogeneous are the same. And so for this chi-squared test of homogeneity, you are testing to see if two or more groups have the same distribution of counts, same proportion, for the same categorical variable. Okay, so again, this is about proportions, not quantitative, not about averages. For example, maybe we are wondering if particular age groups are drinking milk at the same rate. Yes or no. So you've got not just one or two, but you have three particular groups that you are seeing if they are drinking milk at the same rate. Hence, homogeneity. Okay. So now, here's another example, and I want you to think back to our M&M's example, where we had peanut butter M&Ms and peanut M&Ms and regular M&Ms. Now, we had stated, because I had called the M&M company, that those rates of colors actually were at slight bit different rates. So what we could do, had we not known their particular rates, is we could do a test. We could have a sample of those three kinds and test to see if the colors occur at the same rate amongst the bags. Okay, so I kind of want to just do a little theory concepts right now with you. I want to first talk about this stemming from just a one proportion z-test. If the M&M's company said that, 10% of the sample should be 10% of all M&Ms should be red, then you could get a sample and you could get, the counts and see if 10% of your sample was red. Okay? So in that case, this is just a one proportion z-test where you would just check a number of counts against a claim and see if the proportion is what they say it should be. But we know that on Monday what we did was we said, because you all picked one particular type, you picked peanut butter or peanut or regular, and you did a chi-squared goodness of fit test because you did multiple one proportion tests. You said, I'm going to check the claim for not just red, but I'm going to check the claim for all of these colors. So you checked for multiple chi-squareds at multiple one proportions at one time, and that was the chi-squared goodness of fit. Okay, now next step. Let's say we were just interested in comparing peanut butter M&Ms to peanut, and we were comparing the red proportion for peanut butter to the red proportion of peanut, and we were going to check and see if those happened at the same rate. Are those two proportions the same? Well, guess what? That's what we used to do when we did a two proportion z-test. Is the proportion of red in a peanut butter the same as the proportion, the proportion in the peanut butter the same as the proportion in the peanut M&Ms? Okay, that's what we were asked earlier in the year. Well, guess what? if you have many of these two proportion z-tests going on at the same time, that's what we are doing today. A chi-squared test is multiple two-proportion tests. Okay? The other day, our goodness of fit was multiple one-proportion tests where we were just testing one group against a claim. But now we're testing two groups against each other for many categories, for all of those categories, for not only red, but orange and blue and green and yellow. For all of those at the same time, we're checking two proportions all at the same time. That is a chi-squared test. Now, when we're saying, are they the same? That's when we're doing chi-squared test of homogeneity. All right. But I want to extend this one more time and say, you know what? You also, with a chi-squared test, are not limited to just two proportions. You don't have to be only peanut butter and peanut. You can also be peanut butter, peanut, and regular. So essentially, I am doing multiple proportions, and I'm doing all of them multiples of multiples. Okay, so what I really kind of am doing is, you could even think about doing, um, you know, you could think that what you're doing is, say, let's say this. You could say, you could do this problem as a chi-squared test. Turn your head sideways. Here is the red, and I could say, here is what I observed in this group, and this group. And then you could say, here is what I expected to happen in this group, and this group, and this group if they were all the same. So you could kind of think of doing a goodness of fit test. But if you do multiple goodness of fit tests, that's what's happening here. Multiple goodness of fit tests at the same time for all the colors, then you also can do that. You can do a chi-squared test not just for comparing multiple two proportions, but you can compare multiple proportion z-tests. That's kind of like saying you are comparing, you are doing multiple chi-squared goodness of fit tests at the same time. Okay, so mind blown. All right, in summary, you can have one proportion z-test and a bunch of them. That's the goodness of fit. You can have two proportions, but you can have a bunch of them. That's the chi-squared test. And finally, you could have many chi-squared goodness of fits, and thank goodness that's not another thing. That's not like what we're doing Monday. That's just all done the same way as a chi-squared test. So that's chi-squared test. Okay, so that's where we are headed. That's what a chi-squared test is. So now let's talk about the assumptions that have to happen for a chi-squared test of homogeneity. These are still the same for the independent tests. Here we go. All of the assumptions and conditions are pretty much the same as what we had previously done. We would need to say that all the groups are chosen randomly. But here's what's new. You have to say that the groups are independent of each other. Okay, do you remember when we did two proportion tests? We would have to say the peanut butter group is independent of the peanut group. okay? Or that, those two samples are independent of each other, meaning no peanut butter M&Ms are in the peanut M&M group. It's the same thing. So that's the only thing that we're adding, which we are used to adding that when you have multiple groups. Okay, that's just another for example. Um, and so likewise in the M&Ms problem, there are no M&Ms in 2 or 3 of the classification groups. There's not an M&M in the peanut butter, peanut, and regular. Okay, the other difference is degrees of freedom. So that's the other thing. We do not just do categories minus 1 as we did in the goodness of fit. Okay? Because essentially what you would be saying is categories minus 1. Okay? Well, guess what? We have to do categories minus 1 like we used to do, but we don't just have this one column. We also have multiple of those. Therefore, our degrees of freedom are not only categories minus 1 or rows minus 1, they are also how many columns we have minus 1. And you have to multiply those two numbers together. So our degrees of freedom when we are having multiple things is rows minus 1 times columns minus 1. And there you have it. All right, for future reference, I would like to point out that shortly, when we do calculator computation, you can practice it with me, and you don't have to frantically mark it down because I have put the steps here for you. Okay, so the steps are listed here so that you can do the calculator stuff with me. Make sure you have your calculator, and you don't have to write it down. Additionally, I'll reference this as well. I went ahead and wrote how to get your expected value table. Okay, so let's move on to the example. So turn in your notes to the next page, or turn in your packet to page 11. All right. Again, at the top of that, you have those, that's the calculator steps and the expected counts. Okay, so here we practice. I got a nice picture for you here to kind of reference this so you know you've kind of seen these drinks before. So let's go ahead and talk about it, and then I'll talk about my lovely picture I have here. All right, so it is common folk wisdom that drinking cranberry juice can help prevent urinary tract infections in women, UTIs. I'll abbreviate this later as a UTI so it can be shorter. Okay, so in 2001, the British Medical Journal reported the results of a Finnish study in which 3 groups of 50 women were monitored for these infections over a 6-month period. One group drank cranberry juice daily, another group drank lactobacillus daily, and the third group drank neither of those beverages and served as the control group. In the control group, and so now they're listing the results, the numbers that came out of it. In the control, 18 women had at least 1 infection, 20 in the lactobacillus group had at least 1 infection, and only 8 in the cranberry juice group had at least 1 infection. So here's the question. Does this study, remember study is a generic word meaning either observational study or experiment, and I'm going to kind of make you think back to those 2 words here in a second, and we're going to talk, is this an observational study or an experiment? But here's the question. Does this study provide supporting evidence for the value of cranberry juice in warding off urinary tract infections? Okay, so first let's do that quick little review. Would you consider this an observational study or an experiment. Because with your next project you're going to do, after the one that you have right now and you finish that, you're going to do an experiment. But let's see. Let's see. They have these women. It says, I wonder if they randomly assigned them to a treatment group. So they randomly assigned them to a group that drank cranberry juice. So that was one treatment. Another group drank the lactobacillus. Okay, so that was the second treatment. The third, was the controlled. So they were kind of like the placebo, or they did not drink either. So the question is, do you think this is a study? Remember, an observational study is one in which you just have them do something. You just have them, you identify people and then you monitor them. So you're not in particular making them do anything. But in an experiment, you are assigning them a treatment. And so hopefully you recognize that that's what's happening here. And the thing is that you've controlled hopefully all the variables, or as many as you can. You've controlled what you can. You've then assigned them the treatment. And so then, because of that, you can attribute any results in particular to the treatment. Okay, so control what you can, randomize the rest, and then repeat as much as possible. So in this case, they did 50. So hopefully you recognize that this is an experiment. And the right that you have with an experiment is that you can say that the treatment is the cause of the effect. All right, so that's just a review. Let's go ahead and do this problem. Oh, so my picture here, by the way, do you know those like Danimals, or have you seen those commercials for Yakult? Okay, so they want to have the urinary, or the your gut regularity, or so maybe people are drinking this kind of Yakult, or let's see, what is the yogurt, Activia, so that they can kind of make them have the correct bacterial ratios in there, the good bacteria in their intestines. Well, are you going to now risk yourself getting more urinary tract infections? Okay, so maybe that is something they're interested in. So I'm going to move this out of the way so I can do this problem. Here we go. Hypotheses. Your null hypothesis is going to be, of course, that all three groups are getting urinary tract infections, and I'm going to abbreviate that, at the same rate. Okay, so this is the homogeneity. We're checking to see if they are happening at the same rate. So what do you think the alternative is going to be? And we're going to start it off the same. All three groups are getting urinary tract infections, at a different rate. Or you could say the three groups are not getting it at the same rate. Either way. Call it a different rate, call it not the same, whatever. Okay, so now let's do our assumptions and our conditions. So the key is, remember, when we did two proportions, we had to do it for both groups. So when you're doing multiple groups here, you have to do the conditions for all of the groups. So we need to keep that in mind. Okay, our first one, random. It's stated or assumed to represent. And so I think if you look up here, it's not stated. It's not stated. I don't know if they volunteered. They very well may have, but we kind of don't think they were necessarily obtained randomly. But perhaps we can say that, and this may have happened in your proportion that you were estimating, your sample. I guess if they're not randomly chosen, then you are assuming that all three groups are representative And here's a good way to kind of make it a shorter statement of their respective populations. Then I don't have to write it all out. I don't have to say of the um, of all women that take cranberry juice, of all women that take lactobacillus drink, and of all women that drink neither. So of their respective treatment groups. Okay, so I'm trying to make this as short as I can for you guys. All right, so here we go. Independent. N is less than 10% of the population. Independent. And unfortunately, we have to represent that for all three groups. So a lot of times you're going to have different size treatment groups. Here they happen to be all the same, so this is going to kind of seem a little redundant. But I want to do this just to remind you that multiple groups means multiple conditions. So 50 is less than 10% of all women that drink cranberry juice. I'll abbreviate that. Now, you understand that's the population I would be generalizing to. I would be generalizing to and saying, for all the women that drink cranberry juice, and then if you are a woman that drinks just the lactobacillus group, or you're a woman that would drink neither of those, then I'm making a statement about all women that consider themselves in one of those groups. So here I have to list this out for the second one. 50 is less than 10% of all women that drink the lactobacillus drink. Okay? And the third group, 50 is less than 10% of all women that drink neither. Okay? But this has an additional condition. This is the one thing that is new. Do you remember what we have to say? That, you know, the M&Ms are not in all three groups. And what about this? The subjects, or the grouping, or the subject groups. I like that. The subject groups, treatment groups. That's better. Sorry. Not perfect on that. So the treatment groups are independent of each other. I like that better. Treatment groups are independent of each other. Okay, that's the new thing. Now, I'm running out of room here, but this next one actually is going to be kind of short because I'm going to show you where to get this information in a different place. So large enough. What is large enough? So that would be that all the expected, that's the key for large enough. What's expected to happen are greater than or equal to 5. And you cannot just make this statement as if you just like say in your head, oh yeah, I checked them. Yeah, and I checked them and they're greater than or equal to 5. No, you have to prove it to the person that you are showing them this is the case. So you have to compute it all. So guess what? I'm going to show you how to do that now because it's actually quite lengthy. So I'm going to say C expected table, which I think is actually at the top of your next page. Mine is down here below. So let's go ahead and take a moment to do that. So I think you have to actually flip your page. So I want you to do that. Flip your page and let us complete our observed matrix. Has to be a matrix because it's multiple groups. And our expected matrix. So here we go. I'm going to first label them. Okay. So first, in the problem, I know that there were, it told me that, in fact, I think the first thing it said, let me look back, was that 18 women In the control group, 18 women developed at least one infection. Okay, so that would be control group. These 18 got a UTI, compared to 20 in the lactobacillus group and 8 in the cranberry juice group. So I know that this total is 50. Therefore, the remaining cranberry juice group that did not get a urinary tract infection is 42, because those total to 50. And same thing with my lactobacillus. It happened to be the same size group, so that remaining is 30. And with the control group, 50, and then that remaining is 32. Okay, so obviously I know these are different, but they are different enough to call into question that they happen at the same rate. All right, now I'm going to teach you how to get your expected matrix. In order to do that, you actually have to total up the columns and the rows. And I have all the columns as 50, but for the rows, this one totals 46 and this one totals 104 for a grand total of 150. Okay, so if that's what was observed, let's talk about what should happen if these happen at the same rate. And so I'm going to teach you how to find this box's value right now. And I think actually the top of your page or at the bottom of the first page, I don't know, I have this written, that the expected value table can be computed by doing this for each cell. And here it is. You take the row total, which on that matrix, let's see, the row total I think was 46, but we'll do that here in a second, times the column total, which they were all 50. So I'd do 46 times 50 divided by, and for lack of a better word, the total. So the whole entire total of the sample, which was 150. Okay, so let's go do that. So that makes this cell here to be, let's see, what was it? Row total, 46, times column total. Oh, wrong. Yeah. I'm doing this one here. 46 times 50 divided by the total, which is 150. That is essentially saying 1/3 of 46, and that's 15.3 repeating. Okay? Now, if you were to find this one right here, you could either subtract from 50 to find that the remaining is 34.6 repeating. Okay, or you could have also done the 104 times the 50 divided by the total of 150. Okay, again, that's saying 1/3 of the 104. Okay, so that is then what's expected to happen. So I can kind of see the cranberry juice people got a urinary tract infection at lower than expected. Okay, 8 compared to 15.3. All right, you can continue to fill this out by doing all the same computations, but I will tell you that because these are all groups of size 50, because they are all the same size, wouldn't happen otherwise. If these were different groups like 40, 60, and 50, this would not be the case, but because they were all size 50, then what's expected is that they would all happen at the same rate. If they had been different sizes, these would be different numbers here. Okay, so don't think they're always just the same. Okay, so that's observed, and this is expected. And remember, our goal here was to say that all expected counts are greater than or equal to 5. See the expected matrix or this expected table, okay? So, ta-da, there they all are, and they are all greater than or equal to 5. All right, let's name the test that is used. Okay, so what is this today? It is not a goodness of fit, but a chi-squared test of homogeneity. Okay, and of course, next week we'll talk about how to tell the difference between all the tests when you read a problem. We'll have a whole page practicing that. So let's give the test statistic and other pertinent information, your p-value, your chi-squared, your p-value, your degrees of freedom. And so now we're going to go to the calculator. So here we go. I want you to get your calculator out. Okay, and this information is too complex to put in your list. You cannot just go to the list, and I'm even going to clear out what I had. You cannot go to the list and put in your observed and your expected. That's only for one proportion. This is much more complex. So what we want to do is we actually want to go to matrix. So if you look at this right here, x to the negative 1, that button there. Okay, so second, x to the negative 1. And that pulls up all of these options of matrices. There's all these matrices you could use, and we're going to fill in just the first one, matrix A. So I want you to push the right arrow over to edit this matrix, kind of like putting in a list, and hit enter. Okay, so here I am in matrix A. All right, you can see the size that it currently lists it is a 1 by 1. Well, my matrix is not a 1 by 1. Honestly, I can't remember. I think it's rows by columns. I don't really remember. I just generally put numbers in here like 2 by 3 until I find the one that shows the same look as what I want. 2 by 3. Let's see. Yes, that's it. Okay, so it is rows by columns. All right, so now enter in your observed values. And so I'm just going to enter those in, 8, 20, 18, and so on. All right, so I'll give you a second to enter those in to your matrix A. Okay, so once you have those entered in to matrix A, you actually are ready to compute this. You do not have to create a matrix with this expected value in it. It will compute that for you. So all you have to do is go and put the observed values into matrix A and then go run the test. So here we go. Stat, over to tests, and find your good old chi-squared test. Not the goodness of fit test from yesterday, but this chi-squared test right here. All right, so we're going to hit that chi-squared test function, and it says observed. Did you put your observed in matrix A? Yes. Now this expected for matrix B, that's misleading. You do not have to type in your expected for matrix B. It will actually compute that for you. So it's technically not necessary to do that by hand. You can let the calculator do that. So it's as simple as run the test, and there we have a chi-squared value of 7.78. So I'll write that. Our chi-squared value is 7.78. Our p-value was, I think it was 0.02, 0.0204. So I'll just leave it at 0.02. And our degrees of freedom, I think it had said that our degrees of freedom are 2 because it automatically calculates that for you. But I want to talk about that little thing, that little computation of the degrees of freedom. Do you remember from our first page of the notes that degrees of freedom come from rows minus 1 times columns minus 1? Well, if this thing looks like this, then you have got 2 rows, so that's 2 minus 1, times, and you have 3 columns, times 3 minus 1. Okay, well folks, that's 1 times 2, and ta-da, that magic number for degrees of freedom is 2. So that is how that comes about. All right, so now I think we are ready to finish this thing out. We are going to make a decision, compare it to alpha. let's see, our p-value was 0.02, which is less than our alpha, standardized default alpha of 0.05. So what is my decision? P-value is less than alpha. If the p-value is low, then the null hypothesis has to go. So I will reject the null. All right, so here we go. Let's state our conclusion. So since 0.02 is less than 0.05, I reject the null hypothesis. What am I rejecting? I am rejecting this right here. I am rejecting that all three groups are getting urinary tract infection at the same rate. You just restate that. I reject that all three groups get a urinary tract infection at the same rate. Okay? At this point, I stop and I go reevaluate and make sure I'm answering the question exactly. The question is, does this study support or provide supporting evidence for the value of cranberry juice in warding off urinary tract infections? We actually haven't addressed that specific portion of this problem, and I'm going to save that until Monday. Okay, so let's go ahead then and stop right there. We could say, at this point, all we're saying is that there is a difference. On Monday, I'm going to talk to you how to specifically uh, determine that cranberry juice, they're getting a urinary tract infection at a lower rate. So we're going to stop there and actually not do that today. I think that's enough information, and we'll finish those residuals Monday. So, for your assignment, if you would turn to page 17, I believe. Yes, page 17 in your packet looks like this. I only want you to do this first problem this weekend. Okay, so you're going to do this problem only. But I've decided that I want to change this just a tad. So sorry, you're going to have to use your own notebook paper. Oh my gosh, own notebook paper, not in the packet. At this point right here, I kind of want you to go to notebook paper, which of course I'll check that on Monday, for a, guess what, complete phantoms model. Do a complete parameter, hypotheses, and so on. Okay, so just fill out a complete phantoms. Incidentally, you don't have a parameter because there's not like a chi-squared, so you technically don't do that part. You start your test with your hypothesis statements. Okay? All right, so again, your homework, page 17 in your packet, the first problem only. But when you get to parts E, F, and G, on your own notebook paper, complete one full phantoms without the parameter. Okay, thank you. Now, the rest of the class period, let's work on this so that you can perhaps finish that, maybe even not have homework.